I'm Robin Richardson. I'm one of the developers on HemeLB, University College London. And the application today I'm going to do is some simple magnetic drug targeting simulations. So what is HemeLB? Well, like Palabos, it's a Lattice-Boltzmann solver, so it basically does computational fluid dynamics. We also do blood flow. The peculiarity of this code, or rather our selling point for it, is that it's optimized for sparse geometries. So the cardiovascular system in the body is very sparse. What we mean by that is that as a volume fraction, the amount that is fluid is very, very low. So if you look even at the brain, the fluid fraction is going to be far, far less than 1%. And this does actually create some significant problems when you're trying to parallelize this system and do it efficiently across many cores. Just as an example here, we have a mouse retina simulation. So that's just to show you how sparse that can actually get. You've already kind of seen this red blood cell stuff, but it's important to recognize how many different scales you have in trying to model blood, all the way from the epithelial layer, so the blood vessel walls, all the way up to sort of large, full human systems, which we tend to model using one-dimensional systems rather than three-dimensional. But everything I'm going to talk about today is going to be concentrated in this 3D realm here, just Heme, to keep it simple. So the kind of stuff we do with Heme, as actually they do with Palabos as well, is looking at treating aneurysms with flow-diverting stents. So we're interested, for example, in can we simulate the effect that adding a stent will have, actually, sorry, I've got this, don't I? That adding a stent will have on the flow to take the pressure off these bulges in the blood vessel wall called aneurysms, which have a tendency to rupture and kill people with a very high mortality rate if it does rupture, but which are surprisingly difficult to predict. So this one you might think is huge, maybe it'll rupture, maybe it won't, but the size doesn't always correlate with the risk of rupture. Sometimes small ones rupture earlier. So you kind of want to know, will it rupture, and then will the place we're introducing the stent create stress points further afield or something bad? Why do we do simulation? Well, I guess you're all simulators here anyway, but basically because we have this data anyway. When these patients are undergoing surgery, usually to introduce stents, already during this process and beforehand, there have been, for example, CT scans, in some cases MRI scans, which already reveal to us the vascular system at hand. So this would not require more data to be used. This would simply be, what do we already have and know about the patient? Can we give extra information to clinicians? And the kind of stuff so hold on. So the kind of stuff, here's just a few examples. These are the streamlines of the blood flow with this stent introduced. We look at, for example, the shear stresses induced on the wall at the peak of one systole, so at peak of one heartbeat, if you like. So high wall shear stress, or very, very low wall shear stress, or high oscillatory index seems to be associated with the risk of forming an aneurysm. So we think that maybe, say, these red spots might be an indicator, but it's a lot more complicated than that. And we can look at, for example, say the cross-sectional flow, compare that with cross-sections in other simulations and so on. But partly because I thought that the aneurysm thing was going to be done in the last application, then wasn't, I picked a different thing. Something we've introduced more recently to HemeLB is the ability to do magnetic drug targeting. So drug targeting of any kind basically just means trying to concentrate the delivery of a drug in a very specific region. You can imagine, for example, with chemotherapy, that one of the worst aspects of cancer is really the treatment, and that's because it's very hard to get all of the drugs to go to one location. Instead, they end up hitting a lot of healthy cells, which you don't want them to do. So there's a huge number of ways of trying to target it. One we're interested in is using these super paramagnetic iron oxide particles. This is not really being done on humans yet. There's animal trials, and I think there's been one human trial. So we'll see where it goes, but we're simulating it anyway. So the interesting thing about these particles is firstly, the paramagnetic thing just means that applying a magnetic field to them induces a magnetic field inside that material, and that it is aligned with the magnetic field that you're applying, which in magnetic terms will cause them to attract. So that means you can use a magnet to move them around. This is what people would often just call being a magnetic material. But super paramagnetic is because they're very small, so usually 25 nanometers to 50 nanometers. And what that does is it means you can have one single giant magnetic domain, which vastly increases the susceptibility they have to the magnetic field. So it makes them much easier to control and to direct around. And the kind of thing you might do is coat them with polymers, or drugs of some kind, so that they are released at the target site. Or you can simply move these particles to the target site and then oscillate the magnetic field, which induces heating within the particles, and that way you can burn the tumor. Or, for example, it doesn't have to be a tumor, but it almost always is. Here's just a slightly more sciencey diagram of it. So if you have your blood vessel walls here, at the central end of blood vessel, and you've got a number of particles, here's the magnet with its magnetic moment pointing upwards, so that it's a vector. And as you can see, the effect it has on the particles is to attract them, as you might expect. Also causes these particles to attract each other, but you don't see it here. Right, I hope you enjoy long compilation periods because you're doing it again. Okay, so I put all the commands on one page. I'm sorry, but all the commands on one page. And so the first thing to do is to run this horrific looking command here. So first go onto Mare Nostrum, into your home folder. Just if you're already SSH'd in, just type cd tilde, and you'll go to your root of your home folder. And then, if possible, type in this horrifying thing here. This is my shared project. So you should be able to get this folder. This whole command copies the HemeLB folder into your home directory, so you can compile it. Is anyone managing? Maybe it takes a while to even. I should have probably emailed this command to you actually. Yeah. Well, yeah. Okay. So if you've learned the magic of tab autocomplete, please do that. Basically, hammer on the tab key angrily and with frustration while adding extra letters, and eventually it will type it for you slightly faster. That's the idea. Once you do get this, if you look inside this folder, you will find something called readme.md. And if you look in readme.md, you will have all the rest of the commands that you need to run. But you do need to run all of them. I'm sorry about that. Essentially, what we have here is the modules thing is because we tend to use the GNU-C compiler. It does work with Intel normally, but I tried it the other day and there was some obscure error, so I just unload Intel, load GNU basically. And the compilation step looks very, very similar to the Palabos one. You will go to the source folder, create a directory called build, and inside that build directory you will type cmake ... and then make. And then it will waste your time for about 5 minutes while it decides if it's going to compile it or not. Is anyone managing to copy this stuff across yet? Yeah? It takes a while, I'm afraid. I bundled all the dependencies with it because I didn't trust this to work. If anyone's managed to, once it's finished copying, can you let me know? Because it should be. So what I think, let me know once it's finished copying, or if you have a problem compiling, and I'm going to go on just to save a bit of time, just to tell you about what's also in here. Later, if you look, there will be a folder called cases, and inside it there will be one called bifurcation, and this is the test example I'm giving you. But for now, I'll just talk about it. So normally the input we use, I've kind of touched on this already, but is, for example, inject some sort of contrast agent, do CT scans, so X-rays. From that, data, so the clinicians collect this. From that data, you can construct a 3D surface, which we take as being the vascular system itself. And then using some sort of graphical interface, for example, we can tell it where we want the inlets, where we want the outlets to our system. So this can be kind of semi-automated. I mean, you can automate it fully, but you always have to check it because you don't really just get a single surface. You have to pick a contour level, essentially a probability distribution you have, and you have to pick a contour level, and you try and pick one that keeps all the features you expect to be there while not introducing spurious artifacts. So it's kind of, it is rather subjective, and we usually get clinician to look at it and say, yeah, that looks good, or no. The second thing that we need, of course, is the velocity that we're going to input to the system. So at the inlet, what is the speed of the blood? What's its velocity profile? So what you can do is use what's called transcranial Doppler. So it's essentially an ultrasound. So you point this into the patient's brain, and using the Doppler effect, it will tell you what the velocity of the blood is at different points. It's very noisy because the blood's moving at different speeds at different parts of the blood vessel, but you can usually pick the peak and make a good guess at the peak is probably somewhere towards the center, depending on the exact shape. So we can use this. Unfortunately, the skull kind of gets in the road, so you can only really use it for the middle cerebral artery, which is usually just pointing it straight down from the ear, because there is a hole there. And I think maybe some arteries around here, but for the most part, it's hard to get it in other parts of the brain. So we do build, this might not be recognizable as a human, but we do build these one-dimensional models and use that to try and get our input velocities at different points. Is it finished copying it? Is it still taking? Yeah. Oh my God. Yeah. Okay. Yeah. So in the cases / bifurcation, this is where I've put all the input files that you can use. I've not given you one of the absolutely giant things because it takes forever to run. But we'll start with just this simple bifurcation model, which actually, to be honest, does represent blood vessels quite well. It's got one inlet and 2 outlets. And if you want to look at it, if you've got a 3D viewer such as ParaView, you can just load bifurcation.stl, although you'd have to copy it back across to you. Any luck? Has anyone got the? Maybe it doesn't like having 7,000 people copying those files. So it just occurred to me that might be a problem. Actually, well, what's the time?
4:05.
It's fine. Maybe I'll wait. Although if you guys open a second terminal and log into Mare Nostrum, you can actually follow some of the stuff I'm saying here, if you care. The example velocity input file that I've given you looks a little bit like the other ones, although it's made up because it's just for this bifurcation thing. But if you look in the file, there's a file called velocity bifurcation.txt. I wish we didn't call it txt. We should change that at some point. But basically, this file has 2 columns. The first column is the time, and the second column is the speed. So the peak speed of the blood at that time, at the inlet. And if you plot that, you can use GNU plot or whatever you like, but you'll see it looks something like this, although the y-axis might be slightly different because I did increase the speed. So this is the peak speed of the blood at each point. So you've got heartbeats, right? And we call, just for avoidance of confusion, when I say one systole, I'm really talking about, this is a systole and a diastole. So if you say 3 systoles, you kind of mean 3 heartbeats usually. The second thing you might wonder is, well, we've also got something called velocity bifurcation.txt.weights.txt, which is a great name as well. But really, what this is if we've only given them the peak speed, then we haven't really said what the velocity distribution across the inlet is. So it might So here we used a round inlet, so the peak is going to be in the center, but you do get really weirdly shaped or concave inlets. And for those, you have to calculate the weighting accordingly. So because it's circular, you get this parabolic sort of Poisson-style flow, but it can look more complicated. And if you know the distribution from some other code that you've coupled to it, you can use something else, right? There's other ways of doing this. This file just kind of looks, it's the list of sites. So Lattice-Boltzmann creates a regular grid, and each grid point is a fluid site, we call that. So these are just the coordinates of the fluid sites and then the weight to apply. So you'd multiply the weight by the velocity in the velocity input file and use that to tell you what the velocity is at that point. I'm switching between velocity and speed. It's technically speed, but it's velocity along the normal, right? Any luck? No? Anyone finished yet? Okay, I mean, it actually takes longer to copy than it does to compile. That's impressive. So another thing that you'll find in there is the final file that we need, the input.xml file, a little bit like what you saw with Palabus. And what this is the actual file we give to HemeLB to run. And this file has to contain a reference to all the parameters, the Lattice-Boltzmann specific parameters, such as the time step, the number of steps to do, what data file to use, initial conditions, all this sort of stuff. But it also has to contain a reference to any files such as the velocity input file or whatever that you expect. If you look further down inside it, you'll find this part here. So you have to define the inlets and the outlets of your model. So our inlet, we've told it condition type equals velocity. And then we've given the path to that file. And we also have to say the position and the normal of that particular inlet. Something similar with the outlets, although we've really just set them for simplicity to what we're calling zero pressure, which is more zero gradient of the pressure. Then come the paramagnetic particles. So there's a whole section in the XML file called particles, and within each one, you'll see these little groups of subgrid particles, so maybe 500 or so of these. And it's really just telling it the radius of the particle, its position, so what lattice site it happens to be on. So we use that to initialize the positions of the particles. There's other ways of doing this. You can time their release, for example, so it's like they've been injected improperly. But for simplicity, again, just started them off as two spheres. You can also, in this file, change the position of the magnet and its strength and so on. And something about the boundary conditions on the wall, the deletion of the particles when they leave it. I can't see it here, but you can change gravitational constant. The force due to gravity if you're interested. Right, so now, the final step for those of you who've managed to get this far is we're gonna extract the data from this colloid output.xdr into colloids.csv, and then we're gonna copy that to our laptop and then just open Paraview. So is there anyone that's able to do that just now? Yours will still be running, sorry. It should only take about 2 or 3 minutes to run, so it's comparatively short time.
Where does this heme extract?
So the binary is in the bifurcation folder, or it should be. Is it there? Okay, good. You never know what stuff's actually copied across, and it should work. So it's because this colloid output file is a binary file, but this will convert it into an ASCII file, which is easier to visualize. Still running? Yeah. So you'll remember that during the talk about HemoCell, there was some post-processing that was done, and then it just ran through ParaView. I haven't done the post-processing, so you have to do a few extra steps to make it work in ParaView, so you can't ever do anything easily. Maybe I'll just wait for one of the only people who managed to get it to compile. Did you manage to run the heme extract on this?
So the extraction worked is we just
Did it seem to actually create the colloids, the CSV? Cool.
just in some
Oh, you, okay, so if you open ParaView, actually, I'll actually show myself doing it. So the first thing we're going to do is open. Where is it? Oh my God! Mysteriously gone. So also copy your bifurcation.stl down as well, because you need that. So if you copy the bifurcation STL as well, then you can open ParaView. In ParaView, you can open the bifurcation, click apply. So here's the bifurcation. So you're able to see stuff later. It's best to change the opacity. So I'm going to lower that to about 0.4. And then after that, I'm going to open the colloid CSV file. And I'm going to uncheck have headers and change the field delimiter to space because it's not using commas, it's using space. Click apply. This is a terrible. What is this? Right. So now it's loaded the colloids file, and the final step is to go to filters, alphabetical, and table to points, which is not available. Of course, it's not available. Why? Right, so table to points, and then we're going to set the X, Y, and Z columns to field 3, 4, and 5, because those are the columns that contain the X, Y, and Z coordinates in the output. And if you apply that, and then set the coloring to field 0, which is the time, then after an unbelievably arduous journey, you do see these particles. You can see which side the magnet was on because the particles are highly perturbed, whereas the sphere on the side that didn't have the magnet those particles are barely affected by it. So here they do something crazy. Here they don't. So the magnet which I haven't shown is somewhere around here. But in any case, you can see. So this was a simple example. Has anyone managed to do that? That's probably, I think, in the interest of time, I'll just not do that. I'm going to skip this and go straight to what's the point, which was a slide I wrote knowing full well that terrible things would happen to me. So anyway, the point is, why did I give you some silly Y-shaped thing that obviously couldn't tell you anything useful? Well, so what we actually do with this, although it would take too long to actually run during the workshop, is we're interested in doing much larger systems. So to give you an idea how large, these are simulations from the circle of Willis, which is a vascular structure at the very center of the brain that's responsible for most of the blood distribution within it. It's usually about 7 centimeters. We're often interested in it because it's got an awful lot of aneurysms tend to form here. It's a bit more complicated. It's got 3 inlets. So it's got the basilar artery and the intracranial arteries, and then 6 outlets. So these aren't the actual particles. These are just tracer particles to show where the flow is going. It's a bit dark for you, but what you'll see is the flow starting in the 3 inlets and proceeding to the 6 outlets. Make it stop. So here, like with the input files I gave you, we've done something similar, except here we have 3 inlets, so we have 3 input files. We actually calculated these for a number of different patients from a 1D model. So we tried to calculate what those inflows would be for different heart rates and different output, sort of liters per second of the heart. And is there a way I can turn off the lights, just because I know this is quite dark? No. Sorry. So here's an actual particle simulation in the circle of Willis. It's a bit small, but here you'll see that they start. So I started a sphere here, and then you see these guys traveling around. So you see they take a slightly different route from the tracer particles, and then here. So really, you get to see them sort of finding their way through the system. And the reason, so what we do with that is, for example, we might say, here's a target site in this section, and a magnet nearby, and then we can watch the way the particles go through, how they're. You can turn it on if you like. Yeah, sorry. Yeah, and see how they go through this target region, and how that's affected by the magnet. And the reason to do this would be, for example, to get to the actual point, is how do you know how much to inject into a specific patient? So you might want to give them a certain dose, but depending on the location of the target site and the heart rate of the patient, you might want to know to estimate what fraction of those particles will actually go to the target site that you want them. And then you could, for example, we can look at the effect of changing the radius of the particles and the effect on patients at with different physiological states. So the idea is eventually that you would know from just looking at from all this data you already have about the patient, you'd be able to estimate how strong should the magnet be, where should the magnet be for a given target site, what characteristics of particles should we use, this kind of thing, to and then estimate the fraction that will actually reach the target site. Then just quickly, if you're interested in the HPC aspect, you have to pay attention to the difficulty of balancing the load across the system. When all the particles are in one location, they all tend to be handled by a smaller number of cores than when they're all kind of averaged out across the system. So here you can see the time steps per second, so per wall clock time, that the program's achieving at the start when they're all bunched up in one place, versus the end when they're kind of more spread out across the system. So you can see performance hit isn't too bad, but it still matters. I'm just going to quickly finish with, one of the talking points in HPC, which is the Exascale, and that's essentially just referring to the next generation of supercomputers. Our current era is the petascale, because computers are roughly in the region of, say, tens or hundreds of petaflops. So you'll remember Marco briefly mentioned that. the exascale will be anything of 1 exaflop and above. So the US is building them, China's building them, everyone's having a massive race to be the first to build it. It's kind of, the race is just political, but the question is, like, can you do something useful with them, or are they just, So we've been doing some work with Heme, checking how it scales up to large core counts. So you were running something on 8 cores, but here these are things we've been doing on up to 256,000 cores on Blue Waters, which is a supercomputer in Illinois, in the US. Speed up is, so this is what's called strong scaling. It's something that you'll often hear HPC people talk about. It's really just the time taken on 1 core divided by the time taken on n cores. Although in practice, you often can't get the large jobs to work on 1 core, so you typically do them on a larger number. In fact, it's a popular way to cheat. This is to simply make your 1 core job a huge number of cores, because it tends to flatten out the curve. But you obviously shouldn't do that, but people do. You can see here we've done it on 16,000. We did have to do that. It's not cheating here. But anyway, so ideally it would be, 256,000 cores gets you 256 times the speed. In practice, communication costs and so on make that impossible. The other problem that you tend to get is the topology of supercomputers. So there's a German supercomputer called SuperMUC, which is in Munich, that we do a lot of work on. But it has an island topology, so it tends to have about 8,000 cores on each island, and maybe 9 or 16 islands, I can't remember. But you'll find that your communication costs are very cheap within the island, but as soon as you go to another one, suddenly you get this massive performance hit, and it's very annoying. So you have to be careful with that sort of thing. When you create your job scripts, we didn't cover it today, but you can specify certain things about whether you want your nodes to be on a single island, in which case you'll queue for longer, or whether you're going to accept any node as soon as it becomes available, in which case you run the risk of having communication going distantly across the supercomputer, which will make things a lot slower. This is my final slide. This is the thing we're working towards. This is an MRI scan of the full human arterial tree. These are some of the pictures I've shown so far. So this is, like, say, an aneurysm on the order of, say, millimeters. The circle of Willis, which was about 7 centimeters. And then the full human, which is, say, 170 centimeters tall. At least this patient was. So it's just to give you an idea that you see how long it takes to do some of these simulations. Doing one of these giant ones requires a huge number of cores. It has to be very highly optimized, and it will take a lot of time. Just some random numbers I kind of pulled out of nowhere. But segmentation of the files itself, they're already quite large. But voxelization, which is creating the regular grid that lets Boltzmann takes to do its algorithm on, can take, say, 10 hours plus on thousands of cores for this sort of thing. You run into huge memory problems due to the sparsity. It's a massive pain. And then when you run this, you get out terabytes of data output. Sometimes it generally takes longer to create the input files and to process the data than it can do to run the simulation itself. And people typically don't mention that when they're telling you how fast their code is, but actually it's often a limiting factor. And so you can see running some of these simulations can take just several days. It depends how long you want to run it for, but you're killed by 2 things, right? Because it's not just the increased size, it's the fact that the characteristic timescale of a process in a larger system is typically longer as well. So if you make your system, say, 100 times larger, it's likely that the timescale over which things happen is at least 100 times longer, in which case you end up having to some insane amount of extra time needed to run that. Anyway, here are some of the perpetrators of this. Most of this was me and Alex, but all these people have contributed at some point. We probably don't have time for that, but anyway, thanks very much for listening. Yeah.